Welcome to Lesson 10B. Example, the Mercury Professor. Today's going to be a review of an example problem in the textbook. I call it Mercury Prof because it has to do with a professor that was in an office that had mercury. This is example 511 in the textbook, and I would urge you to read this on your own in detail. What's good about this is that it's a combination of practically everything that we've discussed in this course so far. So it's a real good review problem. The background is my co-author of the textbook, Professor Robert Heinsohn. He had done some expert witness consulting for legal trials that had to do with indoor air quality. This problem is based on an actual case that he dealt with. We won't name the university or the professor or anything like that. Definitely the longest example in our book, but also the most interesting. I'm not going to read the whole thing to you. Again, you can do it yourself. But what happened was there was a lab where they stored mercury. Some of it spilled into the floorboards. Liquid mercury forms little spheres that were laying down under the floorboards in this kind of dead space between the floorboards that had some gaps in them. And then there's just a dead space 8 inches to the floor joists. And so the mercury just sat there for 35 years or so evaporating. And so there was mercury vapor in the room. This professor died of mercury poisoning, and his family was suing the university saying that it was their fault. So there was a lawsuit. Professor Heinsohn was called in to calculate whether their lawsuit had validity to it. Was there really too much mercury vapor in the air or not? You all know how to do pretty much everything we do here. It's just a review of all the stuff we've been talking about. Infiltration versus no infiltration, etc. What we're going to do is 3 analyses. Number 1, we're going to compute the maximum possible mercury vapor concentration. That's important because if the maximum possible level was under the PEL, then we wouldn't have to do anything else. So we have to see if the maximum exceeded the safe level. Analysis 2, we're going to try to predict it a little more accurately. It's complicated because there was a window added. They had mercury in a storeroom, and then it was converted to an office in 1945. And he used that office till he retired. And then there was a window added sometime in the 1950s. They didn't know exactly when. So we have to look at the amount of ventilation in there due to exfiltration, infiltration, etc. So this is all the kind of stuff we've been talking about. So how much mercury was in the room between these dates when they found it? In 1991, they remodeled, they tore up those old floorboards and found this mercury. Some of it would have evaporated, so we're doing kind of a worst case scenario for that. And then analysis 3, we're doing the ventilation stuff that we've been doing to estimate 3 different cases with no exterior windows. And then when they added a window, sometime in the 50s, we'll call it 1955. And then in 1982, they added a forced ventilation system. So we'll look at all 3 of these cases. Here's all the details. We have the volume of the room, floor area, the height under the floorboards. That'll be useful for our evaporation calculations. And then we have the PEL, very small for mercury. It's a very hazardous thing. PEL is 1.2 times 10 to the minus 2 ppm. Analysis 1, an absolute upper limit is, let's suppose that the mole fraction of the mercury was the same as its vapor pressure ratio over atmospheric pressure. So we look up the vapor pressure of mercury, 0.0012 millimeters of mercury. This is a worst case scenario. YSS is about 1.6 ppm, but the PEL is 1.2 times 10 to the minus 2 ppm. So this is much higher. It's greater than the PEL by a factor of about 130. So that's definitely a problem. If you convert to mass concentration, you get 13 roughly milligram per meter cubed, well in excess of the PEL. So I want to highlight that this is an upper limit. If this upper limit turned out to be less than the PEL, no further analysis would be necessary because the university wouldn't be liable if we'd say, hey, this is the worst possible case and it's less than the PEL. Unfortunately for the university, it was greater than the PEL by a factor of 130. So we have to continue the analysis. Analysis 2 is to estimate the amount of mercury vapor in the room. So here's a review of the evaporation stuff. Mercury is a liquid that's evaporating, just like we had in containers and in puddles. So we know how to analyze that. We're going to pretend it's in a container this container is the space between the floorboards down to the joists of the room. The only difference is that it's in a bunch of little spheres. So these were spheres of approximately 5 millimeters in diameter, and they were uniformly dispersed in the dead space. So this mercury had spilled over the years, and then it just stayed there evaporating. We came up with this equation. You have to create an equation, and you're used to doing that. We simply have the rate of change of mass here equal to a source, and then there's a sink, the evaporation rate. So this is the rate of mass balance for the liquid mercury. Then you can come up with another expression for the evaporation rate. The surface area of the drop times the number of drops times molecular weight times this molar flux. Remember, we talked about molar flux. So what we're doing is we're pretending we have this situation like we had with the open container. And then instead of just some liquid surface at the bottom, we have all these little droplets, but they are evaporating, and you get an NJ, which is this NHG here, evaporating vapor. We know this distance, delta Z. We're going to ignore the fact that these are all drops. We're going to take the whole surface area, pretend it's a big area there from adding up the surface area of all the drops. We know the surface area of a spherical drop, and we can set S equals 0 because we'll assume that all that mercury was spilled before the professor got in the office. From then on, all it did was evaporate. So S is 0. Number of drops is the mass over the mass per drop. When you put everything in, we get this equation for the rate of loss of liquid due to evaporation. Whatever rate you're losing liquid, that's the same rate of mass that you're gaining into the room because it goes up through the floorboards into the room. A lot of calculations. We calculate the mass of a single drop in kilograms, and then the molar evaporation rate. Remember this equation from chapter 4. We need this binary diffusion coefficient. This equation is one that we didn't talk about, but you can look up DHG, mercury is HGA in tables, or this is a simple approximation for that we used in this problem. We have the DHJA, and then we plug into the YAM equation. The concentration of mercury is so small, that turns out to be roughly 1. The calculations are then fairly straightforward after that. The actual mole fraction is only in the order of 10 to the minus 6, so this is very small. And then you can calculate the molar flux. That's the evaporation rate in terms of moles per square meter per year. And then we can get that in terms of mass. The final equation, when we put everything in, we get an equation in the form of, surprise, surprise, first order ODE in standard form. This one's really easy because B is 0, and we plug in all the parameters to get our A. We're using years here. The only data point we have is 1991. That's the year that they did some remodeling and discovered this mercury, and they measured its mass. And so we use this as our reference data point, 1991. And so that's kind of our T0. But the key is that you can go forward or backward in time. We're used to only going forward in time with all our other examples. Well, we have to actually go backwards because he was in this office from 1945. So we go backwards in time. We have to go back to when he was in the office. The equation's still valid. So that's the important equation. And then you can calculate the amount of liquid mercury in the room in different years. 1945, 42.2, 1980, 40.5. Compare these. This is pretty amazing that there's only approximately a 4% loss of liquid Hg in 35 years. Mercury does not evaporate rapidly. That's probably the biggest underestimate statement in our entire book. 4% in 35 years. So you could really just call that a constant if you wanted without much loss of accuracy. And then we give some justification for some of the things we approximated. So that was analysis 2. And now once we know the evaporation rate, we can analyze the ventilation. Analysis 3 is to estimate the mercury concentration in the room air for 3 different ventilation rates. We're going to make some approximations, etc. And the bottom line is, without spending too much time, we get the same ventilation equation for a simple forced ventilation system. We're assuming it's well mixed, and there's negligible wall loss. There will be infiltration and exfiltration, and those are just going to be included in Q. from previously, we have an equation for the evaporation rate, which is now the source. So m dot vapor equal m dot liquid evaporation. Whatever is evaporating from the liquid is going into vapor. So we have that same equation we had before from the analysis 2. Of course, the real CSS is 0. If you go to infinite number of years, you're going to have no concentration because it'll all evaporate. But we're going to do what we call a quasi-steady analysis, meaning at any year, especially since things are changing so slowly, in a given year, we're just going to assume everything's a constant. And that way we can solve for what we need for each year as a quasi-steady state value. And so the rest of it is just plugging in our approximations, and we get these solutions, answers, YSS, as a function of year. This C is just a collection of constants. And so now let's do the 3 different cases. Infiltration with no windows. When he first moved in to the office, he had no windows. Now, of course, there had to be a door, but this is kind of a worst case, only about a half a room air change per hour. And then when we added an exterior window, we looked at the type of window it was back then and got another half of a room air change per hour. So the total Q for the first case was 25 meter cube per hour. The second case, B here, is 50 meter cube per hour. And then when they added the air conditioning and the ventilation system, we got that up to 59 meter cube per hour. Here's a sample in a certain year, 1945. We get this constant, and then we get 0.027 ppm, which, by the way, is more than a factor of 2 above the PEL. So that tells you that there could be a problem here. Case A is an upper limit. Case B is a lower limit. We'll see how these compare with the PEL. The bottom line is the concentration was above the PEL for either ventilation rate A or B, and C was lower. This can be seen graphically. You can see everything's changing just very slowly through the years. The red dashed line is the PEL, and you can see that ventilation system with no window A here was way above the PEL. So this is considered hazardous. B was just a little bit above the PEL, so it could be hazardous, but there's a lot of approximations made here, but just barely above the PEL. And C, if they had had the ventilation system in that whole time, it would have been a little bit below the PEL. I could add on this plot the best prediction, best estimate. From 1945 to 1955, he had no window, so he was way up there. At 1955, they added the window, so he jumps to this part B, and it stayed that way until 1982 when they put in the ventilation system, so it would have done something like that. But he was already gone. He retired before they did that. The bottom line is the entire time this professor was in the office, the level of mercury would have been above the PEL. And he was in that office probably 8 hours a day or more, so that would be a violation according to OSHA. Is the university to blame for the professor's illness and death? That's where courts come in. We can make an argument that the PELs are pretty conservative and all this, but it looks like the university might be liable. It depends on how the lawyers do. What my co-author said happened was they settled the case out of court, and the answer was left to the attorneys.
Yeah, I knew it. Attorneys always get the last word. Yeah.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.